Hello again. In this video we're going to look at the Constexpr If Statement. This came in C++ 17. If you're reading discussions from that time, you may see it referred to as if Constexpr or static if. And this was one of the most requested changes to C++. And in this video I'll try and explain why it's so requested. As the name suggests, Constexpr If allows conditionals to be evaluated at compile time, as opposed to the plain if statement, which is evaluated while the program is running. So this allows us to write expressions like this: if Constexpr a less than b, and provided that a and b are constant expressions, this will be evaluated at compile time. So if a is less than b, then the compiler will evaluate this code and compile it into the program. And if a is not less than b, then the compiler will evaluate this code and compile it into the program. So the interesting point here is that only the branch which is taken gets included in the program. The other branches are ignored and do not appear in the program's source code as seen by the compiler. So this means we can use Constexpr If for doing conditional compilation. We were already able to do conditional compilation in C++ using the preprocessor directives which came from C. We have the directives #if and #ifdef, and these can be used for conditionally including or excluding code from the compilation. But there are a number of drawbacks to these, which we touched on in the overview of this section. These directives are processed by the preprocessor, which does not understand anything about C++, so it does not understand types or C++ syntax. It can only do simple text-based substitution. It does not evaluate any arguments, so we can have problems involving operator precedence and expressions with side effects. With Constexpr If, this is executed by the compiler during the compilation, so it has access to everything that the compiler knows about C++ and the program. In particular, it knows about type information. As an example, we're going to use a function which returns a string. It can obtain the string either from a library string, in which case it just returns the string directly, or from a built-in type, in which case it calls the toString library function, which will return a string containing the same digits as the argument. We have to use a conditional because the toString function does not have an overload which takes a string argument, so if we try to pass a string to this we would get a compiler error. So we need to know the type of the data that we're using for the string. So we'd have some pseudocode which looks like this. If the argument is a string, then return it directly, otherwise call toString and then return whatever that gives us. And then we're going to write this as a template function which checks the argument's type traits. And if you're not too sure about that or the syntax, then don't worry, this is just an example. So we could have a function which looks like this with the usual C++ if statement. Then we have this bit of template metaprogramming code. Don't worry about this, it just means that if the parameter is a string, then this will be replaced by true. And if the parameter is not a string, then this will be replaced by false when the template is instantiated. So let's try that out. So here is our template function with the if statement. We have some code which calls it. First of all, we call it with a argument of type int, which is built in. Int is not a string, so this will be replaced by false when the template is instantiated. So this will call toString. Then we call the function with a string argument, so the parameter will be a string. This will be replaced by true when the template is evaluated, and this will return the argument directly. So let's see if this works. And no, it doesn't. We get lots of compiler errors. The reason is when we have an if statement, C++ says that all the branches must compile, even if they're never taken. And in this case we have this compile time expression, so the compiler will know that this branch is never taken if we have a string argument, but it has to check it anyway, and because there's no overload with a string argument, this does not compile. However, if I have a C++ 17 compiler and I change this to if Constexpr, then this expression is evaluated at compile time. So if we call this with a string argument, this will evaluate to true, and the compiler will only evaluate this branch and include the result in the program. It will completely ignore this, and it won't even try to compile it. So it doesn't matter what you put in here when you're instantiating it for string. And the same applies for int in the opposite direction. And there we are. So now it compiles and runs. So the problem with the runtime if is that all the branches must compile even if they're not taken. If we have a built-in parameter, then we can't return a built-in from a function which is supposed to return string. And if we have a string argument, we can't call toString because that doesn't have an overload with a string argument. When we have Constexpr if, only the branch which is taken needs to compile, and the compiler will completely ignore any other branches. So what did people do before C++17? One way to do this was with a template specialization. So we have a generic template which will take any parameter type and call toString. And then we have a specialization for string. So this will overrule the generic template, if you like, when we have a string and just return it. So here we have the two template functions. We have the general one, which will call toString, and then the specialization for string, which just returns it directly. When we call this function with a built-in argument, the compiler will instantiate this template because this one does not match at all. When we call it with a string argument, the compiler will look at this one, which does match, but then it'll decide that the template specialization for string is a better match. So it'll instantiate the function which just returns the string directly. And that compiles and runs. Now, this is real black magic stuff. This is not recommended for viewers with a nervous disposition. This is really well beyond the scope of this course, so if none of this makes any sense, don't worry at all, just completely ignore it. You won't be needed to do this again in this course. So template specialization works if you have simple conditionals, but in the more general case, it doesn't really work. There's a trick which relies on something called sFine, which stands for substitution failure is not an error. So when you have overloaded template functions, the compiler will only consider the ones which instantiate. If one of these overloads cannot be instantiated, then the compiler will just ignore it. So the idea is that you have one template function for each case, and then you make sure that the compiler can only instantiate it if that case is true. And then in the second bit of the twisted logic, there's this feature called enable if, which you can use for switching instantiation on and off. So all this means in effect is compiler, do not instantiate this if the parameter is a string. And this is actually a simplified version using some syntax from C++17. If you're doing this in C++11, it's even worse. So as I say, just and then we have another overload, which is the inverse. So the compiler will only instantiate this if the parameter is a string. And then when we call this with a int parameter, the compiler will see that this one instantiates and this one does not. So it'll just ignore this template function and instantiate that one. If we call it with a string argument, the compiler will see that this one cannot be instantiated, so it will ignore it, and it will just instantiate this function. So, alright, so let's weigh up these different approaches. With a template specialization, you need to write several template functions which need to be in a specific order, and this only really works if you have fairly simple logic. With this sFine and enable if, you have complex and obscure code which is difficult to get right and hard to maintain. And finally Constexpr if, so you can just write a single function which has normal looking code, just like any other C++ function, except it's evaluated at compile time. Okay, so that's it for this video. In the next video, we'll have some examples of how to use Constexpr if, but until then, keep coding.